Hey everyone. In this lesson, we're going to finally look at friction. This beforehand, but anyways, here we go. So we're going to look at friction. We're not going to pretend it doesn't exist anymore. A lot of times, friction really is negligible, but clearly it's not all the time. So we're going to start to be able to deal with it. So we're going to look with level forces for now. So the normal force will just be the force of gravity you'll see. And then obviously in the previous lesson, we looked at what happens when you push at angles. So we'll incorporate that in the next lesson. But for now, let's just focus on the concept of friction itself, which is basically resistance to motion, right? Rather than inertia being resistance to changes in motion, friction is just resisting any kind of motion at all and brings it to a stop, basically. And so what fundamental force of the four that we know of is responsible for this? Well, if you look at the atoms and molecules, there's going to be charges. And so when they're close to each other, you can set up attractions. You can actually think of repulsions as being a source of stopping movement as well, because if you try to push this block to the right, the repulsion would work against you. All of these are holding on. You've got this electromagnetic forces between all of the charges. So there's two types. There is friction for when the block's at rest and friction when there's movement. The reason for the difference is when a block's at rest, you get lots of electromagnetic attractions, repulsions set up. Whereas when it's moving, you basically end up with a lower amount because it's like sort of an average of the attractions making and breaking as they're pulled apart from each other and new ones form and so on. So this one, when you're at rest, is called static friction, and the when you're moving is kinetic friction. Okay, so this one makes sense, it's going to be a larger value. This one makes sense, it's going to be a smaller value based on what I said. And it actually works in experiment. Okay, so this is a block being pulled. And so, the force sensor wasn't quite at 0 here, but you can see the force went all the way down to like 3 to get it going. And then it leveled out at around 2.5. And that was pulling with a constant, well, close to constant, around 2.5, right? Newton force to maintain constant velocity is what I did there. And it looks just like this, right? So this person here is showing the idea of pulling this mass along this table, and it has a spring scale, and you're going to see the spring scale shoot up to around 17 or 18 and then levels out at like around 12 to just keep it sliding. So again, here goes up to like 18 or so and then stays around 12 just to keep it moving at a constant rate. And so that's static friction and kinetic friction being shown. So what is the relationship between the force of friction and the normal force? Well, what determines force of friction? It turns out that there's a very easy to understand relationship between force of friction and just the normal force. That's all you need. Okay? And it turns out that they are linear related. So it's linear, and so that means that the friction is directly proportional to the normal force. Okay, so it looks like that, right? Well, when you ever have a direct proportional situation, the slope is your proportionality constant, right? So you have force of friction divided by the normal force equals the slope, whatever that number is. Well, that number is just a number that tells you how much friction there's going to be. So it's called the coefficient of friction. So it's the constant proportionality, which is in this case your coefficient of friction. Okay, and so you're going to have two different ones for the different scenarios, but either way, it's a coefficient of friction. So it's either the green slope or the red slope, right? And so the letter they use is like a curly U. It's actually called mu. It's a Greek symbol like alpha, beta, gamma type thing. Okay, so mu is the letter that's used for that. And so we know mu equals the slope, which is force of friction over normal force, which simplifies to be just the force of friction equals mu Fn. Ff equals mu Fn is what they say. You've seen this before too, where we had like the amount of acceleration you get is proportional to the force. And so the proportionality constant, of course, that determines how much acceleration there will be is the mass. And with universal gravitation we saw recently too, the amount of gravity is directly proportional to the masses and inversely proportional to the square of the radius. And so the proportionality constant there was really that universal gravitation constant, G. Right? So all these things would be very measurable. Just like this, you graph what would it be, force of gravity versus the masses multiplied together divided by the distance between squared, you get a nice straight line. And that straight line would have a slope of 6.67 times 10 to the negative 11 in the case of the gravity stuff, like we saw recently. All right, so, just basically between surfaces, there's a very specific coefficient of friction, right? Static being the bigger ones and kinetic being the smaller ones. So a little joke for you here. So an experimental physicist performs an experiment involving two cats that seem pretty similar on an inclined tin roof, slippery, right? So two cats are very nearly the same, they're the same weight and size and so on, and puts the cats on the roof at the same time and lets them go. One of the cats falls off the roof first, and so obviously there's some difference between the two cats. What's the difference? Well, one has a greater mu, right? So the one with the greater mu is the one that doesn't slide off as fast, or maybe doesn't slide off at all. Is a joke because mu, the letter mu looks like this, right? Well, I'm trying to write with the mouse, but yeah, mu. All right, and one other little clip for you here from Big Bang Theory. Here's a little clip. Oh.
Hello.
I slipped in the shower and I think I dislocated my shoulder.
Not surprising. You have no safety mat or adhesive stickers to allow for purchase on a surface with a low coefficient of static friction.
Low coefficient of static friction, meaning how grippy, how much friction force there is between your foot and the bottom of the tub, right?
What?
Tubs are slippery.
I slipped.
Anyways, so here we go. We've got a calculation that we can do. We've got a 3 kilogram block of wood resting on a wood floor. You're either given the coefficient of friction or you look them up. If you're looking up, it says specifically do a static friction, or it might have told you that, the wood's just sitting there and then you're going to try and push on it and get it to move. It would imply static friction is one you need. So we have F equals mu Fn, in this case, specifically the static coefficient of friction. Because this is a situation where it's just sitting on a level wood floor, we've got acceleration in the y direction 0, therefore F net in the y direction is 0. Therefore, all of the forces that are on it in the vertically, which is just gravity and the normal force, are 0 as well. And so you subtract Fn from both sides, and really we lead to this obvious conclusion here that the normal force is the same as the gravity force, just in the opposite direction. So that's, that's good to be able to show that. You don't necessarily show it every time, but you should be able to if you're asked to, for sure, right? And so we just have negative Fg, which means negative of mg, which means negative of 3 times the negative 9.8. So negative of down means up, of course. And yeah, so I end up with 11.8 newtons. It's the friction force. So it ends up positive. I said up, but I mean, this ends up being obviously the force of friction. So that's a little bit of a, the directionality thing here. It's not in the same direction as the normal force, right? So I suppose some might argue that you shouldn't really have the vector symbols on here because it's not truly the same directions, right? Have directions on that one too. Yeah, I did. But, it's just force of habit, right? But there is a direction involved, but the direction is based on your logic in the situation, not based on the direction of the normal force. So that 11.8 newtons is the static friction force that is available. It can be up to that amount, right? So we'd say, that's the available amount, and if you push harder and harder, the friction force will build up to that amount before it, kind of fails to keep things stationary, right? That'll come back. We'll look at that soon here. We'll get to something tricky about that soon. So determine the force of kinetic friction. Well, same kind of stuff, just the smaller number, right? So we certainly could have just taken this value for the gravity again, plugged it in, and multiplied by 0.2 and gives you 5.9. So again, that if we were to look at that further, we could point out, if I asked, what force is necessary for constant motion, then we'd say, okay, well, to have acceleration in the x direction be 0, then we'd need F net in the x direction to be 0. And so we'd have F net, the x direction equals the applied force that we're wondering about, plus the friction force. And so we'd have 0 equals the applied force plus this like negative 5.9 number, because friction is always against the motion. So if the direction of the applied force is positive, by definition, the friction is in the opposite direction, in the negative. And we just add both sides and we get 5.9, right? So it just basically the same kind of logic as up here, where we should be able to figure out, forces needed for certain motions. Okay. Yeah, but the main question was just, let's just get rid of that. We don't need that. But actually, I could put that back. In this situation here, if the block is moving along, it has this friction force on it, right? And so it would be accelerating. It would be accelerating due to the friction, but the accelerating in quotes, of course, it would be in opposite directions, right? And so if you had, this is a separate situation, so I'll get rid of that. Distinguish here for constant velocity. That's this stuff, right? So that's that work. And then, if sliding freely, let's put this here, if sliding without a force, then the block is going to, slow down. Basically, we're saying, well, F net would just equal FA on it, or FF, sorry. And so we would have MA equals the 5.9. And I don't remember if we had the mass for this thing. Yeah, we did. So it was a mass of 3, right? So we have the 3, and we divide out and get the acceleration, right? So this here, I would divide out and say, okay, the acceleration is going to be, and so on. Now, I'd probably have a minus here, just the idea of it's opposite the direction of the net. It's opposite the direction of the motion, right? Anyways, so divide by 3 both sides and you get your number, right? So the acceleration would be equal to negative whatever that number is, meters per second squared, right? It would be slowing down. So we'd have a positive velocity and we'd have a negative acceleration. I should have started the whole thing there, maybe. Right? We'd have a positive velocity and we'd have a negative, and so obviously for those go together to be slowing down. Just run through how that kind of looks and feels. Okay, so the trick to watch for here, right? If we apply an 8 Newton force onto this thing from rest, analyze that. So we've got friction. The static force friction was calculated to be 11.8. The applied force is 8. And we're looking for the acceleration. So as usual, we're going to say, okay, we're looking for acceleration. So let's work with F net, right? And so F net force is all the stuff added up. And so we've got F net equals the applied force plus the friction force. And so you might just slap numbers in here and say, okay, so we end up with this net force of negative 3.8. Okay, this is wrong and wrong here. Okay, so the negative 3.8 and the negative 11.8 is wrong, because what that would mean is the block's sitting there and there's, friction force available of 11.8. You come along and you push on it, and all of a sudden it accelerates towards you because you pushed on it. That's obviously not going to happen, right? And so the trick is to realize that this friction force is up to, it's up to that, it's able to be up to that amount, right? And so this number here, really what you'd have is you'd have a net force of 0 on this thing, right? You'd have really the friction force would just apply that 8 on it. So the friction force would become negative 8 to match the positive 8 and result with 0. Is really what would happen. Okay? So if you're pushing with less than the friction force, it doesn't cause acceleration against the push direction. That's just illogical. So static force, friction can be as much as, right? And so on. And so, you get rid of this full big static force and you say, okay, instead it's just going to match the push, right? And so we end up with the 0, like I said. All right. If we're pushing while it's sliding, So let's analyze that one. So we're going to push with 8 newtons. Again, it's very similar work, right? So we're going to have an 8 Newton push, and we're going to have a 5.9 friction. Obviously, we end up with this net force of 2.1, and so F net equals ma, and we can calculate out, we're pushing on it while sliding. We're managing to speed it up a little bit, okay? So you can picture a net force forward based on those. You had your applied force, and you had your friction force lined up. You can tell the net force, visually here, you can tell the net force would be this, right? F net. We do not put that arrow on our free body diagram though, right? You think of the net force as the result of all the forces that are on the free body diagram. And moving on here, what about if we push with 3 newtons, okay? So while sliding. So in this case, we've got, again, all the forces adding up. We got the applied force and the friction force. We've got a 3, and this one's capable of being 5.9 and will be because things are moving here, right? So this is, the friction force is going to be that maximum value because we've already gotten to that, beyond that maximum value to get it going and so on. It's going to be that maximum value the whole time. Just like this block when the person was pulling it, right? It stayed at the 12 all the time while pulling. So that gives us this negative 2.9. Well, then we calculate out that it's going to have an acceleration of negative 0.96. And so obviously it's slowing down. Right? The velocity direction was positive, so the acceleration is the opposite of friction. And, the other thing you can do, you can always solve for a third variable, right? So one of the other types of questions would be if they gave you the force of friction and they gave you the mass, or if they gave you the normal force. Obviously it's the same thing if you don't have complications, right? If it's just level forces, certainly the normal force is just the same as gravity. So you could solve for that coefficient of friction. So if we knew the normal force is 49, then we say, okay, well, then the coefficient must be divide out the 49, right? So it's just simple math here where we're just putting in the known numbers. And this one's just slightly more complicated because they gave you mass first. So then it's first get this and then realize that your normal force is the same as your gravity force, just the opposite direction. But the main point of this slide is if you're given this and given this, you can get the coefficient of friction. So that is the new stuff for the day. These are all basically like that. This one here is one of those ones where if you're given a couple things here, right? You're told it's going constant velocity. So that way you're just like, okay, so F net in the x direction is 0. And so really what you have is the 0 equals your applied force plus your friction force. And we're saying, the applied force was 3.5. And so this question, I just wanted to make sure you're able to start tackling it, right? You're going to subtract 3.5 from both sides, and you're getting that your friction force is this number, right? That's the logic implied in what they're doing there. A lot of people would just jump right to saying, okay, so obviously the friction force is negative 3.5, but you really should show how you get to that. All right, so I just want to make sure that we can focus on friction work here, but have the skills needed get to that point, depending on what you're given at the start. These ones down here are ones where you might have to pay attention to, you're nodding and ending up with a negative acceleration because of a push forward. And then these ones are optional because 4 is really the same as 3. So if you want more practice, go for it. And then this one is the same kind of stuff, but first you'd have to get acceleration from uniform motion analysis. So again, I wanted this lesson or this work to be focused on friction, but these are, this one anyways, good to have that stay fresh in the mind. So I didn't want to not show it to you, but I'm just not requiring it. So just 1, 2, 3 for sure, but if you want to do more, it would show initiative and help you be successful. So not a bad idea. Those are good things generally. So there we go. I'm done for today on that stuff. If you have any questions, take advantage of the ways that you can get help. I tried my best to respond right away. I think it's always been less than 24 hours, right? I haven't had a post help questions post for a while, but send by email and then I'll put them in there if needed. But yeah, hopefully that's good. Talk to you later. Thanks for watching.